working? It is? All right. So here we go. So they're saying that magnetic field's uniform. Now, the key, introduce a current, either connected to the motion of the bar will change the flux. Ah, this is it right there.
What?
The motion of the bar changes the flux. Okay? So, what is happening to the flux in the loop, if you will?
Oh, the loop is rising.
Yeah, the flux is increasing. And it's increasing in what direction? Yeah, it's increasing into the page, right?
Yeah.
So then what's going to happen? There's an induced EMF that opposes that change. As the bar speeds up, the induced EMF will get larger until it equals the battery's EMF.
It gets larger?
Yes. Because like the faster, because like, remember what I said, if there's no friction, which there isn't, why doesn't this just accelerate? And if you had infinitely long rails, then you would ultimately reach the speed of light, right? And break the time barrier. But that doesn't happen. Instead, that there's a constant velocity. Well, if there's no friction, then the constant velocity must be a function of what this chapter is about, right? So then what you have to sit back and look at it and say, okay, what's happening? There's this kind of rectangle that's getting bigger. Oh wait, it's getting bigger, there's more flux. The flux is increasing into the page. So there must be Lenz's losses. I'm going to fight that change, right? So I'm going to get something called a back EMF. A back EMF is an EMF in the opposite direction that reduces the efficacy of the battery. So then if you keep pushing this thing faster and faster, the EMF keeps getting bigger and bigger because the delta phi is increasing. You know what I'm saying there? So then when that EMF matches the battery's EMF, then it will just move at a constant velocity. Because it's like you've canceled out the battery. You get what I'm saying? Questions?
So basically what happens is that like as the area of the loop gets bigger and bigger and bigger, then and there's more like resistance towards the acceleration, towards the velocity of the bar, and like there's this, and like the acceleration decreases to zero.
I would phrase it slightly differently. What I would say is the bar is going faster and faster. It is accelerating. That acceleration is causing delta phi to increase, right? So like the flux is getting bigger and bigger. And then because the flux is getting bigger and bigger, Lenz's law says we're going to get, Faraday's law says we're going to get an EMF from that. And then the EMF, the current goes in opposite direction. So the EMF fights against the power of the battery. So that as the acceleration, there's a certain acceleration doesn't go up, there's a certain acceleration. And that acceleration is causing the velocity to increase. As the velocity increases, then the flux increases, and then that causes the back EMF. The back EMF gets bigger and bigger until it matches the front EMF of the battery. But when that happens, there's no net force and you get constant velocity.
So I understand that the bar accelerates, but it's just that like even though the bar accelerates faster and faster and faster,
it doesn't accelerate faster and faster. Its
velocity
increases.
gets faster and faster, but then its acceleration goes down over time because of the back EMF.
Yes. So it's like the acceleration keeps getting ticked away until the acceleration reaches zero, and then the velocity is constant after that.
So you get a really powerful battery and it's really long rails, then you can basically take a very
Yeah. Well, there are such things as magnetic railguns, so, but then they don't work like this. It's not one big giant one because if it was, it wouldn't work. It would do that. It would peter out, and then you'd be using the back EMF that you're creating would be eating up the energy you're pouring in. So you'd just be wasting energy to get to some top velocity. So the way railguns work is kind of like, imagine that like these are electromagnets, and then they can flip. They can be north and south or south and north. And then I am a magnetic, like, whatever, projectile. So then that one says whatever, something. Let's say, the front of me is north, the back of me is south. that will become south. So then I get attracted. And right when I get to the edge, when the attraction is maximal, it like pauses and flips. So now my back is south, this south pushes me this way while this one's pulling me. And then that one turns off.
That's insane.
So it's like, and so every time I pass, this one's pulling, this one's pushing. And then I leave and it's gone. And then this one's pulling, this one's pushing, and it keeps going.
And that's how I'm gonna real
Yeah, that's how a railgun would work now.
a rail gun and a
Gauss gun is different. A Gauss gun doesn't shoot a projectile; it shoots like a beam of ion. Well, technically you could, if you had a big enough piece of metal, you could. But the things that I've seen, which is interesting, it's kind of like a blaster. There's this kid here who made one. He played with it for like 4 years. He loved it. He made a science fair project and everything. Because it would consume the piece of wire. Like you would put a piece of wire in it, charge up these capacitors, and then fire it. And when he did, the wire would disappear. Because there was so much current passing through the wire that it vaporized it. And then he used the magnetic fields to focus it. So it basically shot like a blaster beam. Nah, it barely could like turn a piece of paper brown.
Oh, is that what it does?
You know, like barely tinted the paper brown. Okay, well this, why am I talking about this?
It was a-